This is Chapter 2, Exploring Data with Table and Graphs. Section 2.1 is Frequency Distributions for Organizing and Summarizing Data. Again, we have a lot of vocab words that we need to have memorized for our exam and quiz. So frequency distributions is a table which lists each category or classes of data and the number of occurrences for each category of data. Classes, this is going to be categories into which the data is organized. And you can see in the example right below that we have 1, 2, 3, 4, and 5 different classes. Frequency is going to be for a particular class in the number of original values that fall into that class. We have a lower class limit, which is the smallest value within that class, and the upper class limit, which is the largest value within that class. The class width is going to be the difference between consecutive lower class limits, and it's definitely something we need to know how to calculate. Open-ended is going to be if the first class has no lower class limit or the last class has no upper class limit, like what we see in the example below where it says 60 and older. The next definition that we have is class midpoint, which is definitely one we need to know how to calculate. And this is going to be the sum of the lower class limit and the upper class limit. And again, sum means adding and then dividing by 2. The formula is also listed down here with adding together that lower class limit and that upper class limit and dividing by 2. The example right below this says the number of persons under sentence of death as of December 31st, 2008 in the U.S. is listed in the table below. This is actual data. So the ages are ranging from 20, and then the last class says 60 and older. So the first one says determine the class width. And remember, to determine the class width, as stated up above, it's the difference between consecutive lower class limits. And so if you were to subtract lower class limits, consecutive means one right after the other, we would have 30 minus 20. Looking at those first two classes, we get 10. And so the class width would be 10, and in this case, years. In the table that we have that's given, it asks if it's open-ended for part B and explain. And so yes, it is. We kind of stated that earlier with the definitions. And the reason why is because last class is 60 and older. Part C says determine the lower class limit for the third class. So our third class is right here, and our lower class limit would be 40. Part D says the upper class limit for the second class, and our second class is the one right above that. And so the upper class limit here would be 39. And again, we're dealing with age, so 39 years old. And then it says, is the data discrete or continuous? Since we're discussing ages here, the number is our frequency. That's not what the problem is talking about. The data is on ages of people that are on death row. And since we're talking about age, we know that that's a measurement, and measurements are going to be continuous. Likewise, your age, you might be so many years old. However, you also go down to months and days and minutes and seconds and nanoseconds, and it can continuously be broken down. So constructing a frequency distribution. So this is if you have to do this on your own, which you will have to for your project. Step 1 says select the number of classes, usually between 5 and 20, that you would like for the problem. Calculate the class width, which is going to be found by taking your largest data value minus your smallest data value and dividing by the number of classes that you would like to have for the problem. Then round to a whole number, usually best to round up. Step 3 is choose a value for the lower class limit, the first one. Step 4 is using the first lower class limit and the class width. List all other lower class limits. And then you get this by adding the first lower class limit and the class width to get the second lower class limit, and so on. Step 5 is going to be to write all lower class limits in a vertical column and calculate the upper class limits. Step 6 is going to use each individual data value to calculate the total frequencies that you would have for each class. The next definitions that we have our relative frequency, which is how often something happens, divided by all outcomes. And we also have a relative frequency distribution. And again, that distribution word that we have that was given to us up above is going to be a table of values. So this lists categories for data together with the relative frequencies. So our calculations are given here. We have a few little formulas. Relative frequency for a class is going to be the frequencies for that class divided by the sum of all frequencies. So dividing by the total. And to figure out the percentage, we would take that and multiply by 100%. This idea is going to tie into chapter 4, which is where we discuss probabilities. So on the next page it says the sum of the percentages in a relative frequency distribution must be very close to 100%. They should be exactly 100% or exactly equal to 1 when you add them up. But because of rounding errors, they might be a little bit smaller, a little bit larger. The next definition that we have is cumulative frequency distribution, the frequency for which each class is the sum of the frequencies for that class and all the previous classes that you would have. So below this we have an example. It says the data represents the weights of each of the 2015 men's U.S. soccer training camp members. Use the data to construct a frequency distribution, relative frequency distribution, and a cumulative frequency distribution. So we need to come up with a frequency distribution, a relative frequency distribution, and a cumulative frequency distribution. The weights are listed there. And in order to do this, we need to calculate our class width and also those classes with our lower class limit and our upper class limit. So for exam problems, you would be given how this is going to be set up. If this was a project that you were working on where you had to come up with it on your own, then it would be up to you, and we can all create different distributions, but they would all be, as long as you calculated in those frequencies correctly, they would be correct. So for the sake of this problem, to make sure that it's all doing the same, exactly the same, we're going to go ahead and say that let's have a class width and let's go ahead and say 20 pounds. And I'm also going to say that our first lower class limit is 130. So in order to calculate our distributions, we first need to set up that range of values, and we're talking about weights here. And so that first lower class limit, like I gave you guys, would be 130. And then to find the next lower class limit, we add that class width, which is 20, which would give us 150. And the next one would be 170. And we would continue this process. I also want you guys to note that the heaviest person that we have on this team is 215. And so I'm going to keep going until I make sure that I have that class that would include that heaviest person, which is 215 pounds. So adding 20, we have 210. It looks like that should be enough. I am going to continue this one out to 149 pounds. The next one, and since we don't have any decimals, we don't have to worry about decimal places or anything on those lines, will be 169, 189, 209, and then the last one would be 229. And again, you can always think of that last class as coming out to 230. So that value before it would be 229. And then the next thing is we have to come up with a frequency distribution. So we're going to go ahead and take another column here. I gave you guys these lines to kind of help you organize your numbers and be able to see things a little bit clearer with it. So in order to do this, we have to calculate how many people are in between the range of weight from 130 to 149. So we're going to go ahead and I'll highlight all of these, and this does take some time. If you're doing this on your own, you want to make sure that you are double checking all your work and you didn't forget somebody. And so looking for all the people that are between 130 and 149. So it looks like we have a total of 3. So that would be our frequencies. And then we're going to have to do that for each class thereafter. So next, calculate, highlight, underline something to find all the people that are between 150 pounds and 169 pounds. When you do that, you should arrive at 8 different members of the soccer team, and then 11 in the next class, 3 in the next class, and then 1 in the last class. To get our total and add up that whole column, we have a total of 26, which is, if you count that, that is the number of data points that we do have, so it's a way to kind of check to make sure we didn't forget anybody. The next thing that we have to also do for this problem is our relative frequencies, which again, remember your relative frequencies is going to be taking the frequencies for each class and then dividing by the total. So in order to do this, for the first one, we would take our frequency for this class, which is 3, and divide by our total, which is 26. When you divide this out, let's go ahead and round it 3 decimal places. You sometimes will be asked to leave it as a fraction in simplest form. Other times you'll be asked to round it so many decimal places. So for this problem, let's go ahead and round it 3 decimal places. So this is going to work out to being 0.115. So the next one, we have 8 divided by 26. And working this out, we get 0.308. We're going to go ahead and do this for the remaining ones. The next class, class 3, is going to be 11 divided by 26, which works out to being 0.423. The next class is going to also be 0.115. And that last class is 1 out of 26, which is going to be 0.038. And if we were to sum this whole thing up, we get extremely close to 1. Again, because of those rounding errors, it might not exactly be 1, but it should be really close to 1. The next thing that it wants us to do is a cumulative frequency distribution. And so for this problem, we have to look at our frequencies over here. You can also do a cumulative relative frequencies, which would be the same idea, but using those relative frequencies. So cumulative frequencies, there's going to be that class plus everything before it. So for this first one, it's just 3, nothing is before it. And then the next one, you're going to take your 3 and add in your 8, which works out to being 11. And then the next one, we would do the 3 plus the 8 plus the 11, which is 22. The next one, we're going to do the 3 plus the 8 plus the 11 plus the 3, which is 25. And the last one is adding up all those numbers, and we get 26. This should check to the total amount that you have in your frequencies. The next definition we have right below this is our normal distribution. This is a distribution that starts off with the low frequencies and then increases to a higher frequency and then decreases again. It is also approximately symmetric, and we'll look at this a little bit more in depth in chapter 3. So the next part that we have is combining 2 or more relative frequency distributions in one table to make comparing data easier. So the next example says construct a relative frequency distribution for both types of chocolate chip cookies. And so we have store brand and we also have name brand. And then it says state an observation. So if you look at your table, we have between 18 and 20 chocolate chips. The frequencies when we opened up a pack of those cookies was 8 cookies had between 18 and 20 for the store brand and 6 of the name brand chocolate chip cookies. And so for this, we need to calculate our relative frequency distribution for both of them. So I'm going to go ahead and draw a line here, splitting this. This is going to be relative frequencies, and we'll go ahead and look at the store brand first. And then next we'll do the relative frequencies, but for the name brand. And so again, relative frequencies is where you divide by the total. And so in order to do this, we need to calculate the total for our store brand cookies, which is 40. So for the store brand cookies, the first one that we're going to have is 8 divided by 40, which works out to being 0.2. The next one is going to be 12 divided by 40, which is 0.3. 10 divided by 40, which is 0.25. 7 divided by 40, which is 0.175. And then our last one, which would be 3 divided by 40, which is 0.075. Adding these all up, we do get a total of 1. So check, that works out perfectly. The next one that we're going to do is the name brand chocolate chip cookies. And so our total cookies that we had was 40. And so for the first class, we have 6 divided by 40. And we're going to go ahead and calculate that, and we get 0.15. The next one is going to be 11 divided by 40, which is 0.275. 18 divided by 40, which is 0.45. 4 divided by 40, which is 0.1. And then the last one, which is going to be 1 divided by 40, which is 0.025. Adding these all up, we also arrive at 1, which is what we like. So looking at the relative frequency, or the chance of selecting a store brand cookie with a certain amount of chocolate chips, the largest relative frequency that we have is 0.3, which would mean that is between 21 and 23 chocolate chips per cookie. Whereas if you look at the name brand, the chance of selecting this is 0.45 is the largest one that we have. So it's more consistent. It's a higher relative frequency that we have there. And that is between 24 and 26. So those cookies have more chocolate chips in them per cookie. So relative frequency allows you another way to kind of analyze and look at this. Section 2.2 is on histograms. A histogram is constructed by drawing rectangles for each class. The height of each rectangle is the frequency or the relative frequency of the class, and the width of each rectangle is going to be the same, and the rectangles should be touching one another. One way that a variable is described is through the shape of the distribution. So we have 4 different graphs here. The first one that we have is going to be a uniform distribution, and this is going to be the frequencies of each category are the same, and you can see that in the picture to the right. The height of all those rectangles are identical. They're all the same. We do see uniform distribution sometimes, but more likely we see the next 3. So the next one that we have is bell-shaped distribution. This is going to be the highest frequency occurs in the middle, and the frequencies tail off, get progressively smaller to the left and to the right of that middle place. And it's also considered like a normal distribution. The next one that we have is skewed right, and it says the tail to the right of the peak. So here's our peak up here, is longer. So it's going to the right, skewed right, longer than the tail to the left of the peak. And likewise, skewed left is going to be the tail to the left of the peak is longer than it is from the right of the peak. So to determine if data comes from a population that's approximately normally distributed, a normal quantile plot can be used. The exact process is covered in section 6.5, and we will need to know how to do this for our individual project for the semester. If the data distribution is close to normal, the plotted points will be close to a slope of a straight line. It says below are some examples of histograms and the correlating normal quantile plots. So you can see that that first histogram looks pretty normal or looks pretty bell-shaped, and then you can see that the straight line on the normal quantile plot, the points are pretty close to a straight line. Likewise with the graph below it, whereas skewed right and skewed left have not very straight normal quantile plots. The next section that we have is graphs that enlighten and graphs that deceive. And we have a lot of different types of graphs here that also require you to do some memorizing for your upcoming exam. And so the first graph that we have is called a dot plot. And a dot plot is a graphical display of data using dots. Each dot represents one observation and are stacked in a column over categories so that the height of the column represents the frequency or the relative frequencies. And so dot plots is limited in usefulness, however, it provides a quick picture of data. And the first example on here says Ms. Harper's AP Calculus class has 14 students and the scores for the last exam are listed below. Create a dot plot for the data. And so in order to do this, I'm going to draw a horizontal line here. And this is going to be AP Calculus exam scores. And so for this problem, if we look at our data, it looks like the lowest achieving student did get a 64. And then the highest achieving student did get a 91. Since the data isn't too spread out, it's just between that 64 and 91, I'm going to go ahead and count by ones. If you want, you can count by twos or threes or fives. It does get a little bit challenging though when you're doing that, and you want to make sure you can keep all your data separate. So starting at 60, so we have 60, 61, 62, 63, 64, 65. And then for each of these data points, we're going to make a dot. So 77 is going to be a dot right above the value of 77. 85 also. 73. 64. 90. 80. 81. 84. 96, draw another line out there, 66, 77, and we already have a dot at 77, so we stack the next person, 79, 70, and 82. And so again, this is an example of a dot plot. The next example we're looking at is going to be a stem plot or a stem leaf plot. And this is another way to represent quantitative data graphically. We use the digits to the left of the rightmost digit to form the stem, and each rightmost digit forms a leaf. For example, 147 has a stem of 14 and a leaf of 7. Or 12.3 has a stem of 12 and a leaf of 3. So using that same data from the Miss Harper's AP Calculus class with 14 students, the scores for the last exam are listed below. Create a stem plot. So again, all those values are 60s, 70s, 80s, and 90s. So we're going to go ahead and put down 60s, 70s, 80s, and 90s. And again, this is going to be our stem, and then from here we're going to use our leaves. And so let's go ahead and start with the 60s. So in the 60s we have 64 and 66. And so the smaller one that we have is a 4 and a 6. And again, we already have the first digit, those 60s, written down to the left of the line, and so I only have to write those next digit, which is in the 1 spot, so the 4 and the 6. So for the next one, I'm going to go ahead and highlight the numbers that we have in the 70s. So we have 7, 73, 70, 79, 77. And so we have to write these in the smallest, from the smallest 70s value to the largest. So we have 70, we have a 73, we have a 77, which occurs twice. So we put down 2 7s for 77 and 77. And then we also have a 79. If you notice, between all these values I have spaces. The next one we're going to do is the 80s, so going ahead and doing that, you get 0, 80, 81, 82, 84, and 85. And then the last one we have is a 90 and a 96. This allows us to kind of see where you rank among everybody in the class. It also allows you to see if anything is skewed with the grades, and it gives you a good representation. And again, this is the stem leaf plot or the stem plot. The next example that we have is a time series plot, and this is obtained by plotting the time in which a variable is measured on the horizontal line and the corresponding value of the variables on the vertical axes. Line segments are also drawn connecting the points. The data below represents annual total rainfall in Los Angeles over a 5-year period. Use the data to construct a time series plot. So again, this is the next example that we have. We are creating a time series plot. And so if you notice on this graph, we need to have a horizontal and a vertical axes. And that horizontal one that we have is going to be time in years. And then on our vertical, the data values that we have are going to be annual rainfall, which are in inches. And so looking at our years first, it goes from 2008 all the way up to 2012. So I'm going to write 08, 09, 10, 11, and 12. Those are my years. And then for annual rainfall, the smallest value that we have is 8.69, and the largest that we have is 20.20. I'm going to go ahead and count by 5s on my vertical axes here. So 5, 10, 15, and 20. And again, you can count by any value that you see fit. If you want to count by 2s or anything else. In 2008, there was 13.53 inches of rain. And do the best that you can. Put a dot where you see about 13.53. In 2009, we had 9.08 inches of rain. 2010, we had 16.36. In 2011, we had 20.20. And in 2012, we had 8.69. And then also notice that for a time series plot, line segments are drawn connecting those points. So you want to make sure you're connecting your points with straight lines. And so this is our time series plot. The next type of graph that we have is a bar graph, and this is constructed by labeling each category of data, qualitative data, on either the horizontal or vertical axes, and then the frequency or relative frequency of the category on the other. Rectangles of equal width are drawn for each category. The height or length of each rectangle represents the category's frequency or relative frequency. The other thing to note is that because we're talking about categories of data, this is going to be where our bars do not touch. So bars don't touch. The example says, an 8th grade teacher has 20 students in her science class. The final grades for the 20 students are listed, and there is a list of grades there. Create a frequency distribution and a frequency bar graph of the data. So the first thing to note is that we have letter grades here, so we are not dealing with those numerical values. There is a column in here that some students find helpful that says tally. This allows you to kind of tally them, so you can mark like, oh, there's an A minus and a C and a C plus. So if that helps you to organize your data, go ahead and do that. For this example, I'm going to cross it off and I won't be using it. Counting up the grades, we notice that there are a total of 2 A's, 3 A minuses, 1 B plus, 2 B's, 3 B minuses, 5 C pluses, 3 C's. There are no C minuses, so I'll put a 0 there. And there's 1 D. Counting up our total, we see that adding up those numbers, you get a total of 20, which is the number of students that we have in the class. The next thing that we need to do is construct a frequency bar graph. So in order to do that, we'll draw our axes on here. And the frequency will be on your vertical axis, and then also your grades will be on that horizontal. The grades are letter grades, so we have an A, A minus, B plus, B, B minus, C plus, C, C minus, and also a D. The frequency, they are whole numbers that we're using, that we're counting these frequencies since they are people, and we have the smallest value of 0 and the largest value of 5. So I'm just going to count by ones. And so 2 A's, and we will, for bar graphs, we have spaces in between our bars. So A minus, there are 3. B plus, there is 1. B, there is 2. B minus, we have 3. C plus, there are 5. And the bars should be equal width and equal space between them. It is difficult to do by hand, just do the best that you can. 3 C's. No C minuses, so we don't put anything there, and then there is 1 D. The next type of graph that we have is a Pareto chart. This is a bar graph whose bars are drawn in descending order of frequency or relative frequency. So the bars are going to decrease in height from left to right. So we could redo the graph up above, that bar graph, into a Pareto chart, but instead of it looking like this and going by grades of A, A minus, B plus, B, B minus, C plus, and so forth, we would actually start with C plus. And the reason why is because this is the one that is the highest frequency. And then next we would put, so go C plus, and then it would be A minus, B minus, and C, because those all have 3 values. And then it would go down to A, B, because they both have 2. And then B plus and D both have 1, and then C minus would be last. So we'd rearrange that horizontal axis to fit that descending order. The next graph that we have is a pie chart. This is a circle, and it's divided into sections. I think most of us have seen a pie chart in some class along the lines or in the news or articles that we read. It says each section represents a category of data. The areas of each sector is proportional to the frequency of that category. So we have an example right below that says the table below shows the most common cosmetic surgeries for women in 2009. A total of 1.35 million procedures were performed on women in 2009. And there's the source that says how many surgeries are not accounted for in the data. So if you notice, we have an other category here that is missing that numerical value. So we have a total of 1.35 mil, which is the same as 1,350,000 surgeries that were performed on women in 2009. We do know we were given certain types of surgery in the table, and adding those all up or subtracting them all from that total of 1.35 mil, we do arrive at the number of women that had an other procedure that's not listed, and that's going to be 338,000 women. So in order to create, for part B, our pie chart to show the cosmetic plastic surgeries women had in 2009, we know we have to have a circle. So I'll go ahead and draw my circle here. However, those circles, the sections that we have inside the circle that represent each type of these surgeries, has to be proportional to the amount that we have. So that percentage of them that we have are the frequencies. And so in order to do that, the best thing to do is to calculate our relative frequencies. And for relative frequencies, we have to divide by the total amount. I'm going to go ahead and round these all 2 decimal places. Again, remember your total is up here. It's 1.35 mil. So for breast augmentation, we take the 312,000 and divide by the 1.35 million. And rounding 2 decimal places, we get 0.23. Doing the same thing for liposuction, we get 0.21, and again dividing 284,000 by the 1.35 mil. Eyelid surgery, we get a 0.11. Nose reshaping, we get at 0.10. Tummy tuck is going to be 0.09. And then other is going to work out to be 0.25. And again, that's taking that 338,000 and dividing by the 1.35 mil. So for our pie charts, we have our circle. We can give it a title. This is 2009 cosmetic surgeries. And again, if you want to add more to that, you definitely can. The easiest one to draw in on my pie chart would be the other, since it's a quarter of that circle. So again, do the best that you can. You can label this anywhere that you want. You can write this as a decimal, as that relative frequency, or as a percent, which is a lot of times what we see. So this is going to be other, and I'll go ahead and rewrite that as 25%. The next one that would be the easiest, we just did this one, is going to be that breast augmentation, because the breast augmentation is close to 25%. It's just a tad smaller. And so I'm going to go ahead and label this BA for breast augmentation. And that is 23% of the procedures in 2009 were breast augmentations. The next one that would be the easiest to do would be lipo. I'll abbreviate that LIPO for lipo. And this is 0.21, so it's even just a tad bit smaller. So 21%. And then if you notice, the last 3 are really close in size. So I'm just going to go ahead and split these, and then I'll pick the smallest one that we have. And so selecting the smallest one would be tummy tuck, and I'll put TT here. Looks like the bottom one for me, so I'm going to go ahead and put TT for tummy tuck, and that would be 9%. The next smallest one for me, I'm going to say, is nose, which is going to be 10%. And just make a little note over here on the sides of what I'm calling these. And the last one we have would be eyelid, and this one is going to be 11%. And so adding up all these percentages, we should get to 100%. And again, with rounding, we might be close but not exact. The next type of graph that we have is a polygon. And this is a frequency polygon. And then right below this is a relative frequency polygon. So we're going to kind of look at both of these at the same time. So a frequency polygon is a graph that uses points connected with line segments to represent the frequencies for the classes. It's constructed by using class midpoints and height that's going to be equal to frequencies. And then reading about the relative frequency polygon, it's still using points in line segments. However, we are going to be using not just the class midpoints, but we're also using the relative frequencies this time. And so in order to do our frequency polygon, we are going to create our graph using class midpoints, and then frequencies will be listed on that vertical axis. Likewise, for the relative frequency polygon, we would still have class midpoints on the horizontal, and then on the vertical, we would have relative frequencies. For both the frequency and relative frequency polygons, so for both of these, so part of the definition, we will have to extend ends of the graph on the left and right, so that the graph starts and ends on horizontal line. The next thing that we have is grouped data. And grouped data is putting individuals or observations into groups. This could be like the next example that is saying that there's a range of values here and giving you guys a frequency. However, it doesn't have to be that range of values with the lower class, but for this it would be given where you guys are going to have data and frequencies. And then a little reminder here with the midpoint, because we need to calculate those with doing polygons, you need to take your upper class limit plus your lower class limit and divide by 2. The next example says monthly rain totals in inches are represented in the table. Construct a frequency polygon on the data. So again, with frequency polygons, we do need to calculate those midpoints. And again, to get the midpoints, you need to add together your lower plus your upper class limits, so 2.01 plus 2.75, and then divide that by 2, and you should arrive at 2.38. Likewise for the next class, adding 2.76 plus 3.50 and dividing by 2, 3.13. So make sure to do that for the rest of these classes. You also might notice a pattern too, since these are going to be equal distances apart, and we will talk about that in a second. So once we have our midpoints, we can construct our polygon graph. So drawing a vertical and a horizontal line. And it's a frequency polygon, so I'll leave the vertical axis frequency. And the frequencies here go all the way up to 11, so I'm just going to count by ones. And then on the horizontal, we are talking about monthly rain totals. And this is in inches. And we need to put our midpoints on there, but before we do, I want to start with an extra line. So do not put a number there. We're going to start with the second line, equal space these, and this was 2.38, and I'm just going to put those midpoints in. And then also one last line at the end. So these points, these values that we have down here, we don't yet have those numbers in. However, with polygons, like it was stated earlier, was that the graph needs to be extended down to the horizontal line or the horizontal axes. So we will do that in a minute. For right now, we're going to go ahead and plot these points. So with a midpoint of 2.38, we have a frequency of 5 for that class. 3.13, frequency of 11. 3.88, frequency of 9. 4.63, frequency of 4. 5.38, frequency of 3. 6.13, frequency of 1. And we're going to connect these as stated up above with line segments. So again, do the best that you can. And then once you have your line segments on, we are going to extend the graph down to the horizontal axes, but I need to put those values in. So in order to do that, we need to look at how are we counting to go from one midpoint to the next midpoint. So in order to figure this out, you can take a midpoint and subtract it from the one before it. And when you do, you'll notice that you are adding in 0.75. So in order to figure out this first value here, this starting value, we're going to take our 2.38 and subtract 0.75. And when we do, we arrive at 1.63. So we're going to put in 1.63. Likewise, to find that last value for our midpoint, we're going to take our last class midpoint, which is 6.13, and add in 0.75 since it's after it. When we do, we get 6.88. And so those values would need to be written on there. So this is our frequency polygon. The next example that we have says monthly rain totals in inches are represented in the table. Construct a frequency histogram of the data. So we're in the same data that we had before. And since we have a range of values here, this group data and classes, we need to make sure that we find the midpoints again. And since this is the same data that we had from before, I'm just going to copy down those values from the example right up above. Again, by adding lower and upper class and dividing by 2. And then for our frequency histogram, putting our axes on, we have our frequency. And again, counting by ones. And then putting in our midpoints. Now, we don't need to worry about those beginning and ending lines coming down because a histogram was a bar chart. However, the bars are going to be touching. And so putting in these midpoints, 2.38, equally spaced, 3.13, 3.88, 4.63, 5.38, 6.13, and again, this is monthly rain totals in inches. So the first bar that we have will go all the way up to 5, since that's our frequency. The next bar would go all the way up to 11. The next one all the way up to 9. The next one up to 4. next one to 3, and then that last one will be to 1. So looking at this histogram, our frequency histogram, what do you observe about the two above graphs, our frequency histogram and our frequency polygon? So the data is actually the same. Those midpoints are the same and the frequencies are the same. And if you notice, I'll switch colors here. If you were to set dots at those midpoints on your bars and connect them with line segments, you would have the same graph that you have up above, which is our frequency polygon. And again, extending those ends down to the horizontal. And so you'll notice that the graphs actually give you the same information. They're just two different ways to represent it. So depending on what it is that you're trying to show in your study, you might need to use a frequency histogram, and other times you might want to use a frequency polygon. You'll see both of them, and you'll notice them in different articles when you read. The next example that we have says data in the table represents the number of U.S. residents ages 25 to 74 who have earned a bachelor's degree or higher. Construct a relative frequency polygon. So this time for relative frequency polygon, we still need our midpoints, but we're also going to have to calculate our relative frequencies. So let's go ahead and do midpoints first. And again, you get this by adding together 25 and 34, the upper and the lower, and dividing by 2. And so we arrive at 29.5. The next one, adding 35 and 44, and you get 39.5. Next one be 49.5, 59.5, and 69.5. We also need to calculate, since it's a relative frequency polygon, those relative frequencies. And in order to do that, we need to divide by the total. And so to get that, we have to add those all up, those numbers to get. And we get a total of 54,817. So then taking that frequency for the first one, the 12,967, and dividing by the total of 54,817, let's round 2 decimal places, we get 0.24. The next class, we're going to take the 13,904 and divide by the 54,817. When we do that, we get 0.25. The next one's going to be 0.24. We get 0.19 and 0.08. And then from here, we have enough information to graph our relative frequency polygon. Again, drawing those axes on. And our vertical axis is going to be relative frequencies. And then the horizontal is going to be age, since that's data that we're talking about here. And again, it says age of who has earned a bachelor's degree or higher. So our relative frequency polygon, again, has to have that starting value, and then we'll go ahead and put those midpoints in, which is 29.5, 39.5, 49.5, 59.5, 69.5, and then a last value here. Again, these two last values, we have to put those numbers in, and we'll get to that in a minute. But first thing we're going to do is put in those relative frequencies. The value that we have that's the largest is 0.25, so I'm going to count by 0.05. And again, if you want to count by something different, you definitely can. So for the class 25 to 34, our midpoint was 29.5, and that relative frequency is 0.24. The next class we have 0.25, the next class at 49.5 midpoint. We're back down to 0.24. The next one that we have at 59.5, we have 0.19. And then we have 0.08. And then again, we connect these with line segments. And then those last ones are going to connect down to the horizontal. And then again, to find those values, if you notice our midpoints this time are a lot easier to see. We're actually adding 10 as we go from one to the next. And so that starting value that we would have, subtracting 10 would be 19.5. And then adding 10 to the 69.5, we get 79.5. And so again, this is our relative frequency polygon. The last thing that we have in this section is that graphs can be misleading, and most common misrepresentation of data involves scales of the graph, and inconsistent scales or misplaced origin we will see. So the example right below this says the graph below shows the increase in the housing prices from 1998 to 1999. How is the first graph misleading? So the data is actually identical. It's just represented with graphs that are labeled a little different from one to the other. And so if you notice, this looks like a huge, the first graph, a huge difference between the prices, when in fact it is only gone up a little bit. And you can see that a little bit in the, a little better in that second graph. And so because this, our axis over here, doesn't start at 0, like the second graph does, it's misleading. However, if you were a real estate agent and you were trying to stress that housing prices were increasing drastically, you could represent your data this way. It's not wrong, it's just misleading. And it causes people then to have a fear that the price of houses is increasing drastically, and they might want to sell or buy or something along those lines. The next example right below this has the explanation written for us, but it does say the following graph represents the increase in trash production in the U.S. from 1960 to 2000. Does the graph accurately illustrate the data? And one of the things that we talked about with our charts, especially with histograms and bar charts, our bar graphs, we need to have them be equal width. And if you notice, these trash cans are growing by height, but they're also growing by width. And so it looks very misleading, and that's not very well representation of the data. So it says the trash can used in the picture grows two-dimensional, exaggerating the growth rate. The data grows at about the same amount from 1960 to 1980 as it does from 1980 to 2000. However, the picture appears to have a much bigger increase from 1980 to 2000 due to the picture. So it's just something to be aware of, that data could be misleading. Check the sources that they're coming from and make sure that it's labeled correctly.